Hello everyone, this is Dayuan Tan. I'm very excited to meet you all here virtually at UIC 2021. Today, I'm going to introduce our paper titled TAM, Platoon-based Adaptive Traffic Light Control System for Mixed Vehicular Traffic. The authors include me, Dayuan Tan, and Dr. Mohammad Yunis, and Dr. Vasina Nanoani, and Dr. Shuhyang Li. The reporter is me. So let's begin with some backgrounds. There is an agreement that autonomous vehicles and human-driven vehicles will coexist in near future, because with the development of autonomous vehicles, there will be more and more autonomous vehicles running on the roads. Meanwhile, the lifetime of human-driven vehicles, it can be as long as 20 years or even longer. So we can see in near future, they will coexist. But this coexistence will make the traffic management even harder. Today, the congestion issue has been a problem for many years. What can we do with the more complicated mixed traffic flow? Well, we believe traffic lights will continue to be a major contributor to reducing congestion. Today, there are many traffic light control systems for human-driven vehicles. We deal with them every day. Meanwhile, in recent years, there are many new proposed traffic light control systems, especially for autonomous vehicles. But how about traffic light control system for mixed vehicular traffic? The number is few. That's the problem we want to solve in this paper. So in this paper, we propose an efficiency traffic light control system for AVs and HVs mixed traffic. We consider the mixed traffic, of course, and we consider the traffic flow not only at current intersection, but also at nearby intersections, which can help us better understand the traffic flow, the global situation. In addition, we also consider the platoons of autonomous vehicles, especially connected autonomous vehicles. What's more, we also propose the concept of green light session, which is a new concept. We adjust our traffic light schedule based on green light session instead of cycles, which is usually researchers do. So we have one figure to help us to understand green light session. So the top one shows the traffic lights towards east and west side of the intersection center. And the bottom one shows the traffic lights towards north and south side of the intersection center. And we call this is one cycle. And this, it will be the second cycle. You see also the second cycle. Usually what researchers do is at the end of first cycle, and here they calculate and predict and schedule their plan for next cycle. But here, we don't do this. We propose the concept of green light session. We call this the first green light session. It's actually the first half of a cycle. It includes the green light phase for the east and the west side. And we call this is the second green light session, which is actually second half of the cycle. It includes the green net duration for the north and south set. So what we do is at the end of each green net session, instead of at the end of cycles, we calculate, predict, and then we schedule the next green net session, which help us to adapt to the traffic flow faster and better. And then let's move on to our model, PAM. It's shortened for Platon-based Adaptive Traffic Net Control System for mixed vehicular traffic. It has 4 models, actually. The first model is Traffic Flow Watcher, aka TFW. It observes the traffic at each intersection and connects measurements. The second model is Traffic Net Controller, TLC. It schedules the next green net sessions based on the traffic flow watcher measurements results. The third one is Green Net Extender, aka GLE. It grows current green duration if there barely are vehicles in orthogonal directions. Meanwhile, there is continuous traffic flow coming in current directions. The last model is Platon Coordinator, aka PC. It adjusts the schedule for near future made by the traffic net control when there are Platons exist. And then let's dive into them one by one. So the first one is Traffic Flow Watcher. It actually observes some parameters. Most importantly, there are 4 parameters. The first one is PV. It stands for the number of passed vehicles. So the first ratio is the ratio of number of passed vehicles at current cycle over previous cycle of each flow. If this ratio exists 1, it means the throughput of that flow grows. Then the congestion is unlikely to happen. The second parameter is DV, which stands for number of delayed vehicles. So the ratio is the ratio of the number of delayed vehicles at current cycle over previous cycle of each flow. If this ratio exceeds 1, then that means the load is getting larger with growing possibility of congestions. The third one is AWT, which means average waiting time. So the third ratio is the ratio of average waiting time of current cycle over previous cycle of each floor. If this ratio is bigger than 1, that means the vehicles are waiting longer time. And that means the probability of congestion is growing. The last parameter is EV, which stands for the number of expected vehicles, those vehicles who will come. So the last ratio is the ratio of number of expected vehicles of previous 2 cycles. If this ratio surpasses 1, that means the load in next cycle is expected to rise. More vehicles are coming. Then let's move on to second model, traffic net control. We categorize the situations into 2 cases based on whether there are sufficient remain capacity. So first of all, I will explain what is the sufficient remain capacity. We take this figure as example. So let's say we have the floor from north to south. They will go to the segment, the blue segment here. If the remain capacity of the blue segment is larger than the number of flow from node to source, then it's easy. We will just let all vehicles pass intersection go into the blue segment because it's big enough. Similarly, we can see the blue segment of this third segment. If the remaining capacity of this blue segment is bigger than the sum of flow from north to west and the flow from source to west, then we will just let the vehicles in this two flow pass the intersection and go into this blue segment. That's what we mean the sufficient remaining capacity. But in case 2, when there is insufficient remaining capacity, the situation will be more complicated. What will we do? Over TC, over traffic light control, will dynamically adjust phase duration, and it will consider 4 ratios provided by traffic flow watcher. It will also cooperate with PC, which is Platoon coordinator, when necessary. Okay, and then let's look at this logic figure, which will help us to understand the case 2 when there is insufficient remaining capacity. And also I want to mention that in this case 2, we have 4 subcases. The first step, we will check the ratio of number of passed vehicles. If this ratio is bigger than 1, that means more vehicles passed the intersection in current cycle than previous cycle. And it might be a good news, but we will check out more details. We check out the ratio of average waiting time. If this ratio is bigger than 1, that means we have more vehicles past the intersection, and the vehicle's average waiting time is larger. That means the outgoing segment may be good, but the incoming segment, they might be congested. So we should care about the incoming segments. And on top of that, we check out the ratio of number of delayed vehicles. If there are more delayed vehicles than in this cycle than last cycle, so that will be terrible. Let's combine them together. So we have more vehicles passed, vehicles waiting longer, and the more vehicles delayed. That means the green light duration, the current green light duration is not long enough. We must do something. We must increase the green light duration. And how much will we increase? We just increase it by the average value of these 3 ratios. All these 3 ratios are bigger than 1, so of course the average will be bigger than 1. But if the ratio of number of delayed vehicles is smaller than 1, that means we have less and less delayed vehicles, which will be very good. In this case, we don't need to do anything. And let's go back to the average waiting time ratio. If this ratio is smaller than 1, that will be totally wonderful. We have more vehicle passed, and the vehicle's waiting time is smaller and smaller. That means the incoming and outgoing segments, they are both very good, and they are probably not congested. We continue to check out the ratio of number of delayed vehicles. If it's greater than 1, there are more delayed vehicles, it's okay. But if there are less and less delayed vehicles, that means maybe the green light duration is unnecessarily long. So we need to decrease it. and etc. In our paper draft, we have all these four subcases discussed in details. Then we move to the green net extender. At the end of current green net, if there are no vehicles in orthogonal directions within a certain proximity to the intersection, and meanwhile, there are continuous uninterrupted vehicles flow coming, then the GLE will extend the current green net. And how long will it extend? When there is a Platon, we will extend until the next vehicle of this Platon pass the intersection. When there is no Platon, we just extend it by 3 seconds. The next model is PC, the Platon coordinator. So the principle of the PC is to favor longer Platon and try to keep them intact. Because we know Platon always has better performance. When our traffic net control plan for next green net session, it will generate a plan for next green net session. If the initial plan generated by traffic net control doesn't cut any Platon, that will be wonderful, no action needed. Else, if the plan generated by the traffic net control cuts some Platon, then we have to try to find the minimal Platon cuttings to adjust it. We have this figure help us to explain. For this figure, we have an assumption that in this case, we want to shorten our green net duration for next cycle, for next green net session. And those blue vehicles with edge, they are human-driven vehicles. Those red vehicles with A, they are autonomous vehicles Platons. And this one, this sky blue line, it means the green net duration at current cycle if we don't change anything. And this sky blue line, it means the plan for next green net duration generated by our traffic net control. But or we can say it cut one Platon. We try to avoid this. So we adjust it a little bit to this sky blue line, which has minimum Platon cuttings. In this case, it cuts no Platon. And we will use this sky blue line, which has minimum Platon cutting as the loop plan for next green net duration in next cycle. And then we move on to the validation experiments. We compare the three traffic net systems. They are static traffic net system, which has fixed duration for all phases. They don't change. The second one is actuated traffic net system. What they do is they exactly do what our green net standard does without considering Platons. And the third one is our PAM. This without figure shows the total waiting time comparison. We can say in different simulations with different amount of vehicles, our PAM always has least total waiting time. And in addition, the other two, they increase sharply as the demand leaves, but over time, model increase gently. The second result figure is average waiting comparison. This result shows us that our PAM always has least average waiting time, the best performance, no matter how many vehicles there are in the simulations. And actually over time reduce the averaging time by 75% and 33% compared to the other two traffic light control system. In addition, it also has a more stable performance for different traffic flow demands. And everything will be open source at this GitHub report. And I want to thank you all for coming, for your time. Thank you very much. If you have any questions, comments, suggestions, concerns, feel free to contact us directly. I'm looking forward to hear from you guys. And thank you all. Take care. Have a good day.